next lesson is about the definition of similarity. First, I want to rewind to the first module and talk about the definition of congruence. We defined congruence using a series of rigid motions that maps one onto the other. In this lesson, we're talking about the definition of similarity. And we'll hit one CCRSM standard, which is SRT2, given two figures, use the definition of similarity in terms of similarity transformations to decide if they are similar. Explain using similarity transformations the meaning of similarity for triangles as the equality of all corresponding pairs of angles and the proportionality of all corresponding pairs of sides. Let's get started. Lesson 12 is about similarity transformations. And the opening exercise looks at these two figures, figure 1 and figure 2, and they are similar to each other. And what do you notice about figure 1 and figure 2? Well, one thing you might notice is that they are both the letter J, or I might say they have the same shape. You should also notice that they are different sizes. And for me, that's kind of the working definition that I use for similarity. It's not the actual definition, it's just how I think about similarity, meaning they're the same exact shape, but they have different sizes. Okay. Now down here we have the definition of similarity. A similarity transformation, or simply put, a similarity, is a composition of a finite number of dilations or basic rigid motions. So we defined congruence using rigid motions, and for similarity, we're using a finite number of dilations or basic rigid motions. So you can still rotate things and reflect things and translate things, but you can also dilate them. So if you use one of those four, then you will get something that is similar. The scale factor of a similarity transformation is the product of the scale factors of the dilations of the composition. Now, let me give you a really simple example. If I have a triangle and I dilate it with a scale factor of 2, and I get one that's twice as big, and then I take that one and dilate it by, this is times 2. If I dilate this new one, I'll call this one T1, I'll call this T2 for second triangle, and dilate the second triangle by a scale factor of 3, then I get something that's giant and goes off the page. Then I could go from the very first to the third by multiplying by a scale factor of 6, or the product of those smaller dilations. Two figures in the plane are similar if there exists a similarity transformation taking one figure onto the other figure. And that's the definition of similar. Exercise 1. Figure 1 is similar to figure 2. Which transformations compose a similarity transformation that maps figure 1 onto figure 2? Well, the first thing you could do is to get from figure 1 to R1 is by using a dilation. It's getting bigger. And we can figure out the center of that dilation by connecting the corresponding sides. So if I call this point O, this point A, and this point A prime, then I can dilate it with center O and scale factor OA prime over OA. Second, once I have R1, I can then reflect it over that line. I'm just going to say the red line. But hopefully you can see that you can dilate and then reflect and get R2. Now, a dilation is a similarity transformation because it's a dilation, and then a reflection is a rigid motion. And so from figure 1 and figure 2, it must be similar because I have a series of similarity transformations that map one onto the other. This video was about the definition of similarity. We talked about similarity transformations and used them to define similarity. We also touched briefly on the fact that the corresponding angles will be congruent and the corresponding sides will be proportional. Thank you for watching.